Let's calculate the delta G naught, and the delta G naught prime, for the ionization acetic acid at the 37 Celsius, the body temperature. Okay, so acetic acid, we know that is CH3COOH, and the acetic acid dissociates to gives off a proton in CH3 COO minus plus H plus. And the equilibrium constant for this reaction is also known as Ka, and the value is known for that is 1.8 10 to the power of negative 5. So that's what we have here, and that's the information that we are going to use to calculate delta G naught and delta G naught prime. So in this case here, what we have to use is the equation that we already know. It's delta G naught equals minus RT natural logarithm of the equilibrium constant, in this case here, Ka. Right? So we have the information. We know that the R is 3.14 joules per mole per Kelvin. Right? The temperature here is 37, so we have to use temperature in Kelvin, so plus 273, so this is going to be 310, so the temperature is 310 Kelvin, right? So the delta G naught is going to be minus 8.314 times 310 times the logarithm of the equilibrium constant that has been given to us in a table. In this case, the exams will give the data bank. So that will be 1.8 10 to the power of negative 5. So let's use the calculator here. You can use the calculator there while I'm doing this thing, so that makes sure that we get in the same place. So we get here, the result is negative, but there is the negative sign here, so we're going to become positive, is 28,158 joules per mole. So that can also be simplified by using delta G naught approximately 28.16 kilojoule per mole. And what this is telling us, the delta G is positive, right? So it tells us that at this condition, at 37, this reaction is not a spontaneous reaction, right? Because the delta G is positive. Scroll up a little bit here. And in order to calculate for the other condition, we use the other equation that we already know. Delta G, in this case here, would be the delta G naught prime equals delta G naught, right? This is a generic equation, delta G equals delta G naught. In our case, the delta G that we want is delta G naught prime, right? Plus RT natural logarithm of Q. So we know here that this delta G naught we already calculate, so we have for this one 28,158. It's always better to have everything in joules because the R is given joules, right? So plus R, that's 8.314 times 310, and logarithm of the condition that you want. What we know about this condition here, remember what was different here? The difference in here is that all the concentrations are normally 1 molar in the standard condition, but in the biochemical standard condition, there are only 2 concentrations that are going to change. One is then, and the most important one, is the concentration of protons, right? So the Q for this equation, let's go back here very quickly and look at the reaction that we're talking about is this one here, right? So the Q for this would be the concentration of the product divided by the concentration of the starch material, sort of speaking, right? So it goes back here, and we are going to add this. So we would have to add here the concentration of H plus times the concentration of CH3CO minus divided by the concentration of CH3COOH, right? So what we have is that this is 1 molar, right? Standard condition. This is 1 molar in standard condition. But this in biochemical standard condition is not 1 molar, it's 10 to the power of negative 7, right? So that's what makes the difference in here. So now we are going to calculate then the same thing here, except that this is going to be log of 10 to the power of negative 7, right? So it's going to be 10 to the power of negative 7. Then we take this logarithm there, and we go from there. This alone is minus 16.1. So this term here, only the second term here, is going to be minus 41,442. And the first term remains the same, so that's 288,158. That's the delta G naught prime that we are trying to calculate. So the result comes out as minus 13,384 approximately joules per mole. Okay, so then you can also express that in kilojoules per mole, which will be approximately 13.38 kilojoules per mole. Almost forgot one very important issue here, the net sign minus. And what did this tell us? This tells us that at this condition, this reaction is spontaneous, right? Under the chemical standard condition, this reaction would be non-spontaneous, right? So that's the difference here. Non-spontaneous here, and the spontaneous reaction here. That's all for this problem.